Hi everybody, today we're taking a look at some properties of functions. I have a couple definitions at the top that we are going to discuss. So a function, we know for every element in the domain there's exactly one element in the range, and that means that the x values won't repeat. A relation is a set of ordered pairs. So it usually looks a little bit something like this, where I have a list of coordinates like that. Domain is the input. It's usually the x values, but we'll talk a little bit about why that might change and be y values. And the range is the output. We know we have some set notation down here. We'll talk about our domain and range in terms of set notation, and I'll also review interval notation, which we talked about earlier in the year. And then zeros, we're mainly looking at real zeros here as x-intercepts. So we'll set y equal to 0 and solve for x for those. Down below, I have a quick review on just equations of ellipses and hyperbolas. We did review that last year when we were remote in Algebra 2, but you might forget. You really don't need to know what these look like. We're going to be finding domain, range, and zeros without graphing them, but it's important to see sort of like if I wanted to find the domain and range, I may have a restriction on the left and the right, or the in the positive wise and negative wise, and I may have multiple zeros for ellipses. Same deal with hyperbolas. My domain and range will change based off of orientation, so I may have a domain where my x values are starting at two different locations and going out, or in a range that would be all real numbers, or it might be reversed. And similarly, we have circles, which the domain and range would look similar to an ellipse on that. And parabolas, we may have a parabola that opens up and down like this one, or this one that a parabola may open left and right. If you need extra time to review those equations and how the graphs look, you can pause the video and check out the notes for those. Okay, so this first one, we're starting off with a rational function. So this here is rational. Right, we just ended that unit not too long ago. So we can find the zeros. Remember, if we find the zeros, we're just basically solving the numerator. So here I have nothing really to solve for in the numerator, so we have no zeros. And then domain and range. For these, in this case, I'm going to, we know the domain is going to be all real numbers such that x does not equal whatever your domain restriction is. So in this case, it's 7. For the range, in most cases, we're just going to say that it's all real numbers except for what my horizontal asymptote would be. I'm not going to get into really ones that would cross the horizontal asymptote. So say this is my horizontal asymptote. I know we know a lot more about these now. We know that we could have pieces that both go up and then it wouldn't be all real numbers, or we have crosses. But in general, this unit is usually done long before Chapter 19, so all of my examples will mainly look like ones where we have a piece down below a horizontal asymptote and a piece up above, and they won't cross over the horizontal asymptote. So in this example, we know my horizontal asymptote would be y equals 0, so we end up with g of x is all real numbers such that g of x cannot equal 0. And if I wanted to write these in interval notation, my domain, it's going to go from negative infinity to 7. I do a parenthesis there because it's not including 7. and then we do this union symbol that basically means like or if you have a gap in your graph, and then you go back from 7 to infinity. And the range is going to look pretty similar. So we have, negative infinity to 0, a union, and then 0 to infinity. For our next one, we have a square root function. So you could either use your knowledge of what square root functions look like from last year. So for example, we know my vertex is going to be at 2, 3, and this will open down because of this negative, and because this x is positive, it opens to the right. So your graph is going to look a little bit like this. So we have 2, 3, down and to the right. So you can model it that way, or we can do it based off of our knowledge of square roots. So I know that my radicand here is going to have to be greater than or equal to 0. So x is going to be greater than or equal to 2. And I know what I get out from this square root would have to be positive or 0. So if I solve for to isolate that square root, we'll end up with negative y plus 3 equals root x minus 2. So that means I know negative y plus 3 is going to have to be greater than or equal to 0. So we get y is less than or equal to 3. So we could solve for domain and range that way, or you can do it based off of the visual back from when we graphed these in Algebra 2. So for zeros here, I'm going to take y and make it 0 and solve for x. So we get 3 equals root x minus 2. When you're solving these, you need to be careful here. Make sure that you're checking out that this here is positive, equal to your square root. Otherwise, if it's negative, you're going to have no zeros. So here I'll square both sides. So I get x equals 11. So that's my 0. My domain we already found. So we have x is greater than or equal to 2. Or if you want to do interval notation, we're including 2 and going to infinity. In my range here, we have y is less than or equal to 3, or that would be negative infinity to 3. If we flip it over here, I have an absolute value graph. So again, you could do this visually or based off of what you know from Algebra 2. So here, visually, we would know my vertex is at 1, 4, and it's going to open down because of that negative. So your graph would look a little bit like this V-shape here, and you can use that to find your domain and range. Or we can go based off of some logical reasoning that we know that the value that we get from this absolute value will be positive or 0. So if it's 0, we have a maximum y value of 4, but then when we get positive values out of this, we'll be multiplying by a negative, and it will be decreasing. Our y values would be decreasing. So our zeros here, I'm going to set y equal to 0. I'm going to isolate the absolute value first. This is another one where you're going to have to be careful. If we can't have an absolute value equal a negative, so in that case you would have no zeros. And then once you isolate that absolute value, you'll break it up into x minus 1 equals the positive case and the negative case. So my zeros, we get x equals 3 and negative 1. And then on my domain, I'm just going to go into interval notation. It's all real numbers, so negative infinity to infinity. And then since our range is less than or equal to 4, we'll have negative infinity to 4 and then a closed off bracket because it's equal to. On D here, this is a graph of a piece of a conic section. So where we would typically be able to visualize this, and you still may be able to visualize this. I'm going to do this purely based off of inequalities and knowledge of square roots. So the first thing I'm going to do is solve for my domain and range. So we know the radicand has to be greater than or equal to 0. So I'm going to isolate x squared to start. So we get x squared is less than or equal to 1. And then when you go to square root both sides, you have to make sure that you're adding absolute values. Now this brings us back to the beginning of Algebra 2, which was also a review of stuff that we did in Algebra 1, which was absolute value inequalities. Remember, when we are taking away the absolute value, you need to turn this into either an and or an or compound inequality based off of your inequality sign. So when it's less than, it's and. If it was greater than, it would be or. So when you go and break this up, it's x is less than or equal to 1 and greater than or equal to negative 1. So that's going to be our domain. So I'm going to do interval notation for that one. And then for my range, because I have y equal to a positive square root, I know that y is going to have to be greater than or equal to 0. So nothing else to solve for here on the range. So we have 0 to infinity for that interval notation. And now I'll go ahead and I'll solve for my zeros. So I'll make y 0 and I'll solve for x. So we get 1 equals x squared. So absolute value of x equals 1. So x equals plus and minus 1. Now I do want to mention something really quickly. If I had something like x equals root 1 minus y squared, in this case my input is my y's and my output is my x's. Since we define domain to be input and range to be output, in this case my domain would be, an interval notation would be my possible y values, which again, -1 to 1, but it's pertaining to y values here, and my range would still be 0 to infinity, but also now pertaining to x values. But either way, regardless, when you're solving for zeros, you're always solving for the x values. So E looks pretty similar, but it is slightly different. So I'm going to again take my radicand and set it greater than or equal to 0. So absolute value of x is greater than or equal to 2 root 2. Remember, when it's greater than, it's going to be or. So that means x is greater than or equal to 2 root 2, or x is less than or equal to -2 root 2. So you got to remember to flip the inequality symbol and make it negative in the second case. So in my domain, if I wanted to do set notation, it would be x is greater than or equal to 2 root 2, or x is less than or equal to -2 root 2. But if you wanted to do interval notation, it would be negative infinity to negative 2 root 2, and then a union, because you have a space, and then positive 2 root 2 to positive infinity. So there's your domain. Your range, again, since y is equal to a positive square root, our range is going to be y is greater than or equal to 0. Or you could have 0 to infinity. And then for my zeros, I have 0 equals root x squared minus 8. So absolute value of x equals 2 root 2. So we get x equals plus and minus 2 root 2 for my zeros. On this next one here, we have a step function, everybody's favorite, a step function. So if you remember, this one looks a little bit like this, where we have -1 to 0, and then here 1. So this is -1, this is 1, this is 1, and it would continue up like that. And it continues in both directions. So in this case, for my zeros, we actually get an inequality for my zeros. So we'll have x is greater than or equal to -1 and less than 0. For my domain, we end up with all real numbers on that, or negative infinity to infinity, because even though we have some open circles here, that value picks up on the next step. And then for my range, we have only integers, right? It's going, -1, 0, 1, 2. So the symbol for integer is sort of like the R. It's, instead of a bolded R, it's a bolded Z. Not sure why it's Z. I'm sure it's from a different language. So we have y values and all integers for that. I'm not as skilled at drawing a bolded Z as I am a bolded R. You can always verbally describe something too. So if you had, say, even integers, you could just write that you have even integers out. And the last one here, this one again sort of looks like examples D and E, but a little bit more complex here. So I'm going to start by solving for my domain. I'm going to set that radicand greater than or equal to 0. I'm not going to expand anything. So I'll subtract 36 and divide by -4. And then I'll square root both sides. And I make sure to add absolute values in my next step. And it's less than or equal to, so we're going to change this to an and. And then I'll solve for x by subtracting 2 from everything. So there's my domain. So you can write it in set notation or in interval notation. We would have -5 to 1, like that. And then my range, you have, you can solve for or isolate the square root if you'd like, or you can think about it logically, since we know we have positive values or 0 coming out of this radical, and then I'm multiplying it by a negative. I know my y values are going to have to be negative or 0. So that's the first way you can find that your range is going to be less than or equal to 0. Or you can do it just like how we did the first square root graph, which was example B, and you would isolate the square root, so you'd get negative y equals root 36 minus 4 times x plus 2 squared, and say that negative y has to be greater than or equal to 0, so that gives us y is less than or equal to 0. And then finally for the zeros, I would set this equal to 0. And square both sides, and then add 36 and divide by or subtract 36 and divide by negative 4. So we get 9 equals x plus 2 squared. Square root both sides. So we get absolute value of x plus 2 equals 3. So x plus 2 equals plus and minus 3. So that gives me x equals 1 and negative 5.